Let's discuss now the basics of boundary layer from the gate point of view. So in this we'll see how, first of all, how a boundary layer is formed, why a boundary layer is formed, and this we have in this introductory lecture about fluid basics we have more or less seen this, but again we'll revise that, and then we'll see what is the type of the regions in the boundary layer: laminar, transition, turbulent, and what determines which will form. And then we'll see some parameters about the displacement thickness, momentum thickness, energy thickness, and the whole objective is to calculate the drag force. Okay, let's see first what is a boundary layer and why boundary layer is formed. Okay, so for this you have a solid object, solid stationary object, and you have a fluid moving over it. So whenever a fluid is moving on a solid stationary solid object, so what happens is, because of the no slip condition that is observed everywhere, it's universal. What is observed is that the fluid layer which comes in contact with the stationary solid surface, its velocity is zero. It does not slip relative to the surface. So that is your no slip condition that is observed for every fluid that goes past a solid. So you can say it's kind of a experimentally verified condition where, or it has come from the experiment, the no slip condition. Whenever a fluid layer passes over the solid, the immediate layer which is in contact with the solid becomes motionless. It doesn't have any velocity. So that is your no slip condition. So what happens is that the first layer, the immediate layer in contact, has a velocity 0. Now this motionless layer slows down the velocity of the layers above it. It slows down the particles of neighboring fluid as a result of fluid friction or because of viscosity. So you can see that the velocity is 0 here, and then the velocity is, if you go in the vertical up direction, the velocity slowly increases. So this effect of this motionless layer is felt up to a certain distance, after which the flow is again everywhere with the same velocity. So this region in which the presence is felt, that region is called boundary layer. Okay, so the region in which the effect of no slip condition, or in which you can say the effect of solid is felt, is called boundary layer. Okay, so the consequence of this no slip condition is that you have a velocity gradient that is set up, velocity gradient that gets set up normal to the solid surface. Okay, and so that is one of the consequence. You have a velocity gradient that is, so consequence of no slip condition. So because of no slip condition you have the velocity, and second is you have a drag force that comes from the fluid onto the solid. So basically, because of this fluid motion, if you keep a solid stationary, so there is some drag force that comes on the solid surface. It tries to drag, the fluid tries to drag and takes away the solid in its own direction. So this is important because, like, if you have, let's consider an aeroplane, okay, which is moving, okay, moving in still air. You have still air. Okay, now this problem you can visualize as a stationary aeroplane and the fluid moving with the same velocity as that of aeroplane. So then you can analyze in the way we have started the problem. So you have a stationary aeroplane surface and the fluid moving with v. That's what happens in a wind tunnel when you so you can't when you simulate all this flight testing and all that, you keep the flight stationary in a wind tunnel, and you move the air with the help of compressor. You compress it and then you move it with very high velocity in wind tunnel. That just to simulate what happens in reality, aeroplane moves in a still air, okay, and here in a wind tunnel. So you're just modeling the same problem in a different way. You're giving now the fluid velocity v and aeroplane stationary. So on this, the fluid tries to drag, right, because I mean the immediate layer which is in contact with the surface of the aeroplane, that becomes stationary, and then the presence is felt up to some layer. That layer is called boundary layer. And so the consequence of this boundary layer, or consequence of the no slip condition, is that you have the velocity gradient set up, as well as you have a drag force that comes on the, so that comes in this direction on the aeroplane. Okay, so now the other way of saying it is when when the aeroplane is moving like this, okay, the drag force is this way, okay, because in a still air, when the aeroplane moves, it tries to, the surface tries to move left relative to the air. The air applies a fluid friction or resistance force due to viscosity, and summing up all those for the entire surface, you get a force called drag force. Now you need to know the drag force, because it's basically against the, it is the force against which you need to work. So all your engine requirements, everything will depend on your drag force. So that's why, and in order to know the drag force, the study of boundary layer is important, because once you study the drag force, once you study the boundary layer, the whole objective is to get the drag force on an object which is moving in still air, or on a stationary object the same way, and the same thing on a stationary object. If the fluid is moving, what is the drag force? So this problem is, I mean, these two problems are similar. Only thing is, in one way the solid is stationary, fluid is moving. In the same way, in the other way, the fluid is stationary, solid is moving, but the drag force that comes is because of the viscosity or because of the boundary layer formation. So that is important. The whole objective about studying boundary layer is to know drag force. Okay, because once you know the drag force coming on an aeroplane, it will be helpful in designing the aeroplane. You can basically, you will get an idea about how much engine power should be there to, so that engine will have to produce this much force to balance this drag force and move with some velocity. So the whole objective is to know the drag force. Just keep this in the background of the mind. So now we'll study first for a flat plate. If a fluid is moving, let's say stream u infinity or v. Now starting just at the start, you will observe that there's a boundary layer formation which is something like this, and if it's a long flat plate, you'll see that after some portion there's a transition region, and after that you have all that turbulent region. So there are three regions in which you can divide the flow. In the starting, some portion of the plate, you'll observe that the velocities are all aligned in one direction. The fluid motion is all organized, it's an ordered motion, and that region is termed as laminar boundary layer, where the motion is all ordered motion, organized motion. You don't have any velocity fluctuation, and in the turbulent range you have all sorts of velocity fluctuation. Basically the inertia effects dominate over viscous effect. If the viscous effects dominate, it is laminar flow, okay, and if inertia effects dominates, it is turbulent flow, okay, and in between you have a transition where not much change, okay, it's a layer between laminar and boundary layer, so that is transition layer. So this is called critical length, beyond which you will have this onset of turbulent. So there are a couple of definitions now. First is your boundary layer thickness. The boundary layer thickness, how it is defined: the boundary layer thickness is the distance from the surface at which your velocity is almost the free stream velocity. So the distance from the normal to the surface, normal to the plate, where your velocity of the fluid is almost the same as the free stream velocity, or it's the point above which you have no effect of the solid felt. That's the one. So it is defined by delta, is defined as distance y from the surface at which u is 0.99, almost 0.99 times of unity, or you have, so all those points on this line, the vertical distance from the plate, this is the plate, so vertical distance from the plate, so where your horizontal velocity or the fluid velocity reaches the free stream velocity, that is the point up to which your effect of the solid is felt, and that is your boundary layer thickness. So you can straight away see that the boundary layer thickness depends on x is the distance along this. So at the start it is 0 and then it slowly increases. So you have different, the way it varies depends on the laminar also, whether the flow is laminar or turbulent. Okay, so that is about boundary layer thickness. So on a flat plate, the way you define your drag force, so you have a flat plate here, so the drag force that comes because of the fluid motion is represented by Fd, and the way it is defined is the coefficient of the drag into your projected area A, so that is your, okay, and then half rho v square. So for this, to understand how we got this, first you need to understand what is the coefficient of drag. So the coefficient of drag is basically your, okay, we'll come to this. First, there are two important things which you should first know. One is your local friction coefficient, and the other is your boundary layer thickness. So the first, boundary layer thickness, you have already defined. The second is local friction coefficients. Let's first define these two terms, local friction coefficient and boundary layer thickness. Boundary layer thickness I have already defined. It's the normal distance from the plate where your velocity reaches the free stream velocity. Now second is local friction coefficient, which basically measures, like if you have a flat plate at this distance x, if my shear stress acting, now remember the shear stress that is acting on the plate will be in this direction, but on the fluid, now the fluid above here, the fluid, so the shear stress on the fluid particle will be in this way towards left, because the fluid is moving towards right. The friction that comes from, or the resistive force that comes from the plate will be in this direction, so your shear stress will be in this direction, but in turn on the plate it will be tau naught will be in this way. If this is the action, this is the reaction offered by the fluid onto the plate. So this tau naught by the dynamic pressure, that is half rho v square, that is defined as the local friction coefficient. Okay, so this is again one of the non-dimensional numbers in this boundary layer. When you study boundary layer, one of the non-dimensional number that comes is tau naught, is local friction coefficient. Okay, and this again depends on your function of x, because your shear stress can change, and this half rho v square is constant because v is your stream velocity, free stream velocity, far away velocity, so that is all constant. So it all depends on tau naught, how your shear stress or wall shear stress or your plate shear stress varies. So we have defined two important factors, two important points, the boundary layer thickness and the local friction coefficient. So these will be useful later when we state these laminar flow equations and boundary layer equations. Another important term that demarks when the laminar will occur or when the turbulent will occur. So that transition from laminar to turbulent basically depends on transition from laminar. So remember, we are doing all this for a flat plate. So transition from laminar to turbulent depends on lot of things. One is your surface geometry, whether it's flat plate or circular dia, cylinder, pipe. On the surface roughness, if it is more rough, you'll have onset of turbulence quickly, and the velocity also. Higher the velocity, more chance for turbulence. Okay, so the Reynolds number is expressed for a flat plate as rho v. The general formula is this: rho v, characteristic length by mu. For flat plate, the characteristic length is the distance along the flow, that is rho v x by mu. So this is the local Reynolds number at a distance from the x is the distance from the leading edge. Leading edge is this, where the flow is taking place. So x is the distance from the leading edge, okay, and v is the free upstream velocity, and it is said that if the Reynolds number, critical number, reaches 5 into 10 power 5, that is considered as the demarcation between laminar and to turbulent. So from this you can get the distance from where you calculate the critical distance where. So if your plate is more than this critical distance, that means you will have laminar, you will have turbulent flow also. So that is one check, like you, because this value has come from experiments that, or even by rigorous derivations you can show that if the critical Reynolds number is 5 into 10 power 5, it's the onset of turbulence. So we can find out the distance from where. So sometimes if the plate is shorter than that, that means you will have only laminar. If the plate length is greater than its critical, you will have turbulence. Okay, so always you have to calculate this. You will express Reynolds number in this way, and you can calculate the critical distance. You can calculate the critical distance at which turbulence starts. So we have seen the local friction coefficient, which is CFX. It is defined as the wall shear at tau naught, and the wall shear, and with ratio of the dynamic pressure half rho v squared. So this varies along the length of the plate, along the length or along the surface of the plate. But we are interested in the drag force on the entire surface, right? So what we do is we take, so this is, so if at a distance x, if this is CFX, so if I take a small length dx, so on this dx the drag force, let's say it is df. So df is the small drag force that is coming on this differential element dx. So how do I calculate drag force? So drag force here is tau naught into, so if say tau naught is the shear stress on this, so tau naught into, so tau naught is tangential into area, it's a shear stress into area. So this length is dx, and the perpendicular width, let's say it's 1 perpendicular unit per width we are taking into the paper. So tau naught is, from this definition, it is CFX into half rho v square dx. So this is your df. Now if I want to find the total force, the total drag force, I can write CFX half rho v square dx, 0 to L, the length varies, the x varies from 0 to L. So I can take out half rho v square constant because it doesn't depend. So CFX dx 0 to L. So this is the general way of calculating the drag force if a local friction, how it varies with x is given. Now this variation will depend on whether it's laminar or turbulent. We'll see later about that later. So most of the time what we do is, it is also expressed in the average sense. So the average friction coefficient will be basically your average will be your average shear stress. So average shear stress will be the total drag force by the total area by half rho v square. So total drag force by area is nothing but F by length is total length L into 1 is the perpendicular width half rho v square. So that is F half rho v square by L, but we already got F by half rho v square from there. So it is 0 to L Cfx dx by L. So this is again a way of calculating average friction coefficient. So importance of this is once you get the average friction coefficient, you can directly multiply that by half rho v square to get the average shear stress and multiply with the area to get the total drag force. Sometimes you always express in this also. Okay, so now let's come to an important topic called boundary layer equations. So we'll not derive this, but I'll tell you the general trend in boundary layer equations. Boundary layer equations, well, the physics is quite complicated because you have the laminar flow, you have the transition, and you have the turbulent flow. Even in the laminar, you have to basically start from the Euler equation. Starting from the Euler equation, and because the flow is viscous, so you cannot neglect the shear terms. So you have to take a fluid particle, write down the pressure terms, write down the shear terms, and equal sigma fx is equal to max, and all that rotational, and the flow is rotational because it's shear, so there is some kind of rotation, so you have to consider all those things, and finally you'll end up deriving equation. But the physics is so complicated, so what is generally done is your dimensional analysis is done. Whenever in most of the one of the useful technique in fluid mechanics or heat transfer is dimensional analysis, because the physics is quite complicated. The response or if physics depends on many factors, it's not simple strength of materials, it depends on many factors. So when you write down the dimensional analysis, you express, let's say the drag force is my output. I want how much is the drag force on an aeroplane. So the drag force will depend on, let's say the drag force will depend on the surface geometry, the surface roughness, the upstream velocity, okay, all that. So it's all, so most of the important thing is surface geometry and the profile, the surface roughness, and the upstream velocity. So on all this your drag force, drag force will depend. So now, because my objective is always the drag force in boundary layer, that's why I am studying this theory. Now the objective of this is, when I do the dimensional analysis, so when I do the dimensional analysis, I can convert this into non-dimensional numbers. So the non-dimensional numbers that come is the local friction coefficient is a function of Reynolds number as well as the surface roughness factor. Okay, and if I want to know this distance, so I can start from that distance y expressed in many other factors, y distance into many other factors. So this normal distance will be again depending on the surface velocity, geometry, all that, fluid velocity, geometry, everything. And when I do the dimensional analysis, I get boundary layer thickness delta. Basically I get everything in terms of non-dimensional numbers. So the non-dimensional numbers that are involved in boundary layer are the boundary layer thickness, the local friction coefficient, and the Reynolds number. So let's write down the expressions. So we have, for the laminar flow, while neglecting surface roughness and all that, the boundary layer thickness is varies as 4.91. this on a flat plate. On a flat plate, these are the equations. Now if you take a flow over the pipe or flow inside the pipe, internal flow or external flow, it will all vary. So this is how it turns out for the flat, for the boundary layer thickness for the flat plate laminar flow. So there are two things of interest: boundary layer thickness, how big the boundary layer is, and what is the effect of the boundary layer? So that is captured in this local friction coefficient, because once you know local friction coefficient, you can get the drag force. That's what we discussed, right? So this is REH half, and all this is valid when REH is less than 5 into 10 power 5, because that is the demarcation. Okay, and for turbulent flow, the boundary layer thickness is 0.38 x into REH varies to the power of 1 by 5, and the local friction coefficient varies 0.059 REH to the power of 1 by 5. So here when the Reynolds number is greater than 5 into 10 power 5. So this is how you'll calculate. These are the expressions which have come from your dimensional analysis. Okay. So one point is, if REH can be written as rho VH by mu, so you can see that delta is proportional to 1 by, or this is 4.91 x by your rho Vx half by mu half. So delta is proportional to your root x in laminar flow, but in the turbulent flow it is proportional to x by x power 1 by 5. So delta is proportional to x power 4 by 5. So this is how it varies. So that you can get from these expressions. Okay.